Nephele project aims to offer a solution for customizable IoT devices, utilizing them to enhance energy efficiency in buildings. The operations of buildings account for 30% of global energy consumption and 26% of global energy-related emissions. Now, while there are many reasons why buildings account for such a big energy consumption, we have been looking at HVAC systems. HVAC systems are critical components of modern buildings, providing temperature control and indoor air quality, but they are also major consumers of energy, accounting for up to 40% of a building's total energy consumption. The reason for this lies in the fact that HVAC systems typically operate on a predefined schedule, regardless of the room occupancy. Predicting the occupancy would enable more efficient scheduling of HVAC systems. Instead of having predefined occupancy patterns in buildings, they should be learned on the fly. For example, they should be adaptable throughout the day and week or just accommodating the common usage of a room at a given time. Given the customization of IoT devices, the challenge lies in efficiently managing on-device applications. Moreover, a modern building comprises of connected IoT devices, thus the openness and interoperability are important topics in the Nephele project. In our demonstration, we illustrate how interoperability and device management can be accomplished using the Nephele solution.
We are going to enhance existing HVAC systems with presence detection. This is achieved by integrating tiny machine learning and micro-complex event processing engines into our IoT devices. We start with building the device firmware in a drag-and-drop manner. Then we add tiny machine learning and micro-CP engines into the firmware. The TinyML engine can enable ultra-low power machine learning on embedded devices while allowing on-device training. The micro-CP engine is designed for streaming event processing on embedded systems. Next, we deploy our firmware to our device, which is a Siemens development board. With that, the TinyML engine can infer the presence by using environmental sensors such as temperature, CO2, and humidity. We improve the prediction accuracy by adapting the model on the fly. Also, we can change the control logic of HVAC systems for better efficiency through sending the rule to the micro-CP engine in real time. Now we showcase a presence detection prototype where we deploy the IoT device in a meeting room. We run the machine learning model directly on the device to detect the room occupancy. The scene is about a colleague enters the room for a meeting, and the HVAC systems will turn on when the detection shows that someone is in the room. The prediction results together with the ground truth and the sensor readings are shown on the right. Here, 1 represents occupancy and 0 represents no occupancy detected. We can see that the prediction of our machine learning model in orange can follow the ground truth in green, generated by a radar sensor with some delays.
We support interoperability by adhering to the W3C Web of Things standard. The field devices provide their capabilities with a thing description with different protocol bindings such as MQTT or CoAP. The virtual object runs on an edge device and implements a Web of Things service supporting heterogeneous protocols. Additionally, we use a thing model to represent the capabilities of a micro-CEP rule. With the Virtual Object Manager, we can enhance the capabilities of a device, creating a composed virtual object by dynamically pushing a micro-CEP rule to a device at runtime. 2 heterogeneous field devices are used: a Siemens Target 5 device equipped with temperature, humidity, and CO2 sensors supporting MQTT protocol, and a CoAP light bulb. Virtual Object and MQTT Broker runs on a Siemens IoT 2050 gateway. Finally, the Virtual Object Manager runs on a Mac laptop. MicroCP and TinyML engines are running on the Siemens thermostat and publishing their data on this MQTT broker. The window on the top is the virtual object. It provides access to all the things. Currently, we don't have anything stored. In the background of the virtual object, there is a lot going on. And on the left-hand side is the Virtual Object Manager, providing a set of endpoints to create TDs or start or stop a micro-CEP rule on the hardware. We can retrieve the thing model of the thermostat using the following endpoint. Here is the description. We also have a set of rules stored in our system where we can retrieve using the following endpoints. For example, the first rule provides a description of the average temperature. Let's enhance the capabilities of our thermostat to also support calculating the average temperature. As you can see, a new thing description is created combining the capabilities of the thermostat and the rule. Now I can access the properties of the thermostat, for example, the temperature, via HTTP. Let's start the average temperature rule on the thermostat. The rule is pushed to the broker via the virtual object, and since the microCP engine is subscribed to it, it can pick it up. And the microCP engine generates a set of events, always publishing the recent average temperature value.